Hey guys, here's a little video to help you with dealing with parallelograms as it relates to being on a graph or with all the coordinates. The good news is all the properties are still true, of course, and the ultimate goal here would be to actually show you how to prove that you have a parallelogram using one of the properties that we know, especially focusing on the coordinates. So for right now, just this is basically a list of all the properties that you could use to get a parallelogram, and the cool thing is you only need one of them. If any one of these actually works, you've got yourself a parallelogram, including this new one, which I made a little star here for, where we're so used to saying both pairs have to be parallel, both pairs of sides have to be opposite sides have to be congruent. But if you actually have a case where one pair is both congruent and parallel, that's just as good. Okay, so we basically have all the same properties as before. You'll notice the consecutive interior angles one isn't really listed here. Technically that could prove it, but as it pertains to the coordinates, we're not really going to use that. In fact, we're not really going to use this one as it pertains to the coordinates either, because we're just not going to have a way of getting any angles other than right angles on our coordinate grid. Okay, so we're just going to focus on the other one. So you'll see. So for right now, we're going to start with parallelograms and use some of the properties with the graph, and then I'm going to show you how to do it the other way too. So this first example is talking about the diagonals, and it's saying to find the coordinates of W, which is the point of intersection of those two diagonals. So I'm sure you could probably just sort of look and try to figure out roughly where it is just because it's plotted for you. But let's try to get the exact value for sure. And the key there is you're dealing with diagonals of a parallelogram. We know something about the diagonals of a parallelogram. They bisect each other. That means they hit each other right in the middle. They cut each other in half. That means W must be the midpoint. Okay, so to find the midpoint using coordinates, we have a formula. Hopefully you remember. If not, here it is. You've got the average of the x's and the average of the y's, and that'll get you your midpoint. So we just got to find the two endpoints that will yield this midpoint, and if we could use S here, which is obviously at the origin. That's a definite. S is 0, 0, and that would be a diagonal all the way up to U, which is 1, 2, 3, 4, 5. Was that 6? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 5. You could technically use TV also, since they both bisect each other. The problem is TV doesn't actually hit a perfect, box here, perfect corner here. So I guess you could probably estimate, and I'm sure it's going to work out if you did. But it is a good idea. I think somebody in period 5 had mentioned it's a really good idea to use the ones that you know for sure, which I totally agree with. So we're going to use the ones we know for sure. So the midpoint W is going to be at 0 plus 6 over 2 and 0 plus 5 over 2. So W is going to be at 6 over 2 is 3. 5 over 2 is 2.5. Let's see if that makes sense. 1, 2, 3. 1, 2, 3, and it's in between, so yeah, 3, 2.5 makes perfect sense. So the key to this one is to recognize that the diagonals have to actually meet at the midpoint. So that's why you would use the midpoint formula. Alright, there's a couple of examples you could try on your own right below. The answer keys on the back, you can try them out and check it out. It's basically the same as this. For these, since the picture's not there, let me scroll up here. If the picture's not there, if you want to sketch it, not a bad idea. Just a quick little rough sketch. Plot it, or grab a piece of graph paper and plot it. But you technically can do this without plotting it, but just might be a good idea if you're having any trouble. Okay, that's the first one. For this one, they're telling you we do have a parallelogram, but they're only giving us 3 of the vertices. So let's plot them and get an idea of what this looks like. 1, 2, 3, 1, that's R. 3, 1. Negative 1, 5 is S. 1, 2, 3, 4, 5, that's S. And T is at 3, 6. 3, 1, 2, 3, 4, 5, 6. T. Okay, and they're telling us there's some V somewhere that makes this a parallelogram. So they're telling us it's parallelogram RSTV. So we have to follow that order. In this case, they are giving us the letters, and they put them in order. So R goes to S, to T, and then there's got to be a V somewhere. Well, that v has got to be somewhere in this range. I'll just kind of like make a pretty big circle here because it's somewhere in here. It's obviously not going to be here or here. It's certainly not going to be down here. If this parallelogram could go in any direction, if I didn't draw this side in, I guess we could have had a point here, or maybe even a point up here. But since the letters have to go in order, I kind of have to follow it. Okay, so how do we figure this out? Well, there's a little bit of a hint up here. If you read the heading, you can use the slope to find the coordinates of the fourth vertex. What do we know about slopes as it pertains to a parallelogram? Well, parallel lines, if you remember, have the same slope. Parallel lines have the same slope. So I know that opposite sides have to be parallel for a parallelogram. That's one of our properties. In fact, that's our definition. So if I can just figure out how my slope is affecting this side, I can sort of just like repeat that slope over here and figure out where it hits. Similarly, I could do the slope for ST and sort of, reenact that slope, repeat it for R to V, and they should match up. So let's check it. The slope, if I do RS here, I'll do rise over run, right? So it looks like I have to go down and over. So down 1, 2, 3, 4, over 1, 2, 3, 4. So I went down 4, over 4. So the slope of SR was down 4 over 4, which is -1. But I'm actually going to keep it as this for now, just for the sake of drawing it. I think it's much easier to do it that way. So I need to go down 4 and over 4 from T to get to V. So down 4, 3, 4, over 4, 1, 2, 3, 4. Here I am. That's V, which is at 3, 4, 5, 6, 7, 2. 7, 2. Let's connect it and see what it looks like, see if it makes sense. That looks pretty good to me. V is 7, 2. And honestly, you're good to go. Let's check it the other way, just to compare. Instead of doing S to R and then copying it for T to V, let's go S to T and copy it from R to V and see if it matches. So I have to go up 1, over 1, 2, 3, 4, up 1, over 4, up 1, over 1, 2, 3, boom. There it is. So obviously I would normally do it twice, but it's a good way to check. And it looks pretty good too. Now we could recalculate the actual, we can obviously calculate the slopes using the slope formula, by the way, just a quick refresher there. y2 minus y1 over x2 minus x1. But I think for a problem like this, it's actually easier to just do it visually. But this will, of course, work too. Once you get the point, you can check the slopes and see if they match. But if I can see what you did, I'm totally okay with that. Okay? Let's see. If that was S. I did do... Oh, I did count it. I didn't actually do it there. Just for the sake of making sure I didn't mess anything up. SR is 1 minus 5 over 3 minus -1, which is -4 over 4, and we're good to go, which is -1. Okay. I just wanted to show you that obviously it would work both ways too. Alright, there's a practice problem for you to try, and if you check your answers in the back, you'll see if you got it right. If not, hopefully you can figure out what went wrong, maybe check with a partner, or let me know. Okay?